Flat panel displays are becoming important, not only in the computer industry, but also for home entertainment, automotive, aviation, and communication applications. Each flat panel display technology has its own features and limitations. Here's an example of a flat panel display. This is an active matrix liquid crystal display. The display looks quite good when viewed head-on, but as one views it from different angles, the quality degrades. Presently, it is not well defined how one measures display characteristics such as viewing angle artifacts. How should they be quantified so that they properly reflect a viewer's perception as being either objectionable or unnoticeable? These types of questions motivate a research effort at NIST to develop standards and measurement practices associated with performance characteristics of displays. This video demonstrates an initial part of our program, which is to model a display on the Princeton engine. The Princeton engine is a massively parallel video supercomputer. Since one of its uses is real-time video processing, it permits us to model a variety of displays. Video is input, processed by the engine, and then output for continuous display on a monitor. Each line of video is input to the engine and digitized into pixels. Calculations are performed on each pixel by a processor to produce the desired change in the pixel. The entire line of pixels is processed at the same time, since there are 1,024 processors in parallel which run the same program for each pixel. This massive parallelism permits the Princeton engine to output the processed line before the next line of video is input. The result is real-time video processing of any video input. The motivation for using the Princeton engine in this application is that it permits us to see what the model looks like. Whatever model we choose to program into it, we can view the results. We are going to first discuss the development of the model and then show its simulation on the Princeton engine. The flat panel model we develop here assumes pixels which modulate the light by exploiting the electro-optical Kerr effect. The Kerr effect was chosen for its mathematical and conceptual simplicity and is not in general being considered for use in displays. However, since the Kerr model exhibits artifacts generic to electro-optical displays, it serves as a prototype upon which more complicated and realistic models of liquid crystal and other flat panel displays can be based. To understand the complications of a display based on an electro-optical medium, we start with a liquid that exhibits the Kerr effect and is placed between two electrodes to form a cell. A light beam is passed through the liquid perpendicular to the electrode axis of symmetry. The beam is polarized at 45 degrees with respect to the axis of the electrodes and can be resolved into two components, one perpendicular and one parallel to the electrode axis. When a voltage difference is applied to the electrodes, an electric field is produced in the liquid, and the liquid becomes birefringent. As the light passes through the liquid, a phase difference is produced between the two polarization components, which is proportional to the square of the electric field. In this example, the phase difference occurs because the polarization component parallel to the field travels more slowly through the liquid. The polarization is accomplished by means of a polarizing filter. With no field, there is no change in the polarization state of the beam upon exiting the cell. However, as the field increases, the effect of the increasing phase difference causes the output beam to be in some state of elliptical polarization with extremes of orthogonal linear polarizations. This cell is made into a light valve by placing an analyzer in the output beam, which has its polarization axis perpendicular to the initial zero field polarization direction. With no field present, no light is emitted from the cell. As the field increases, the light output increases to a maximum when the polarization of the output beam is aligned with the analyzer. If the field is increased more, the light output begins to decrease. Using this crossed polarizer configuration, the transmission through the cell is given by a sine squared function of the square of the ratio of the applied voltage to the voltage required to reach the first light maximum, called the cell constant, V sub m. V sub m is expressed in terms of the plate separation d, the Kerr coefficient b, and the light path length through the cell, L. We draw your attention to the path length dependence, since the path length depends upon the viewing angle, as we will see. The transmission curve then consists of a series of smooth, nonlinear transitions from dark to light and back to dark, depending upon the applied voltage and the effective path length through the cell. To form a display, the cell would have to be very thin, and 3 such cells would be required for a color display. Thus, red, green, and blue filters are added, and the color pixels are sandwiched between a polarizer and an analyzer. Viewing angle complications arise owing to the electro-optical nature of the pixel. Consider first the horizontal viewing angle theta as measured from the normal. The light path through the cell increases as 1 over the cosine of theta. Since the electric field along the path remains unchanged, the net effect is to increase the phase difference in the emerging beam. In the case of the vertical viewing angle phi, as measured from the normal, the light path also increases as 1 over the cosine of phi, but the electric field perpendicular to the light path is reduced by the cosine of phi. The net result is to decrease the phase difference in the emerging beam. All these factors are incorporated in this model of a flat panel display based on Kerr effect pixels. The video supercomputer permits real-time viewing according to the model prediction. Here is the video output of the Princeton engine displaying a real-time panel simulation. On the left is the video as processed by a linear system, and on the right is the video as it would appear on the screen of our model flat panel display. We can illustrate the flexibility of the system in that we can display the source, the processed result, compare half of each, or the entire screens side by side. You will note the increase in contrast and the loss of most shadows. This is to be expected from the shape of the transmission curve. Here is the transmission curve overlaid on the model video. This graphic is displayed also in real time and is included as a part of the model for illustration purposes. The horizontal axis is the voltage applied to the pixel, and the vertical axis is the light output from the pixel, black at the bottom and white at the top. The cyan line represents the linear range from black to white. The red part of the transmission curve is the region being currently used in the model display. Note how much of the red transmission curve falls below the cyan linear line. If we again display both input and output together, we can especially see what is happening if we view the gray scale of the input and the output. Much of the grays of the original are mapped into darks, consistent with the graphic. By adjusting parameters to exploit a more linear region of the transmission curve, we are better able to match the original grayscale. The result is a display which closely matches the original. Viewing angle artifacts can be seen directly also in real time. Here is the effect of a change in vertical viewing angle at 10 degrees, 20 degrees, 30 degrees, 40 degrees, 50 degrees, and 60 degrees. The display simply gets darker. Now we start back at the viewing normal and change the horizontal angle to 10 degrees, 20 degrees, 30 degrees, 40 degrees, 50 degrees, and 60 degrees. Not only does the display brighten, but false negative colors arise. This kind of viewing angle artifact can be a major objectionable feature of electro-optical displays. What is happening is that the used portion of the transmission curve exploits both sides of the first maximum. If this is carried far enough, we can create a negative. Another concern regarding flat panel displays is the resistance in the connections across and down the screen, causing a degradation in voltage signal as a function of position on the screen. Here we show a degradation along the horizontal of 6%, 13%, 19%, 25%, 50%, and 100%. Here is a vertical degradation of 6%, 13%, 19%, 25%, 50%, and 100%. Crosstalk between the pixels is another concern in flat panel displays. Here is a comparison with the original for 12%, 25%, and 100% horizontal crosstalk between the vertically oriented pixels. The results of the flat panel display model calculation demonstrates the utility of the Princeton engine. The model prediction can be compared with the video input in real time as well as in a variety of output formats. The properties of the pixels comprising the display can be input to the model, so the manufacturer is able to obtain an appreciation of how the display will appear when finished before manufacturing is attempted. NIST is providing access to this facility for U.S. industry, government, and academic researchers. We have shown that the Princeton engine can be used effectively in modeling flat panels. This is one component of the NIST flat panel display research effort. Our future plans include assembling a laboratory to make photometric and colorimetric measurements on displays and use the Princeton engine to present realistic models of more advanced display technologies. The apparatus depicted here shows a prototype spectroradiometer or image detector viewing a flat display mounted on a positioning device. A segmented sphere provides a well-characterized surround in order to make reliable measurements of display characteristics. These tools will permit NIST to contribute to the development and maintenance of standards and measurement practices associated with the performance characteristics of display devices.